Imagine you're an archaeologist. You're on a remote island surrounded by ocean in every direction, and you're staring at a stone tool, not a modern one, not something dropped by a sailor a few centuries ago, something ancient, something that, according to every dating method available to you, was made by human hands around 800,000 years ago. And here's the problem that keeps you up at night. At that time, this island was completely surrounded by deep, open water. No land bridge, no shallow coastal shelf you could have waded across, just ocean, miles and miles of it. So how did anyone get here? That's the mystery, and the more you dig into it, the weirder and more wonderful it gets. Here's what makes this different from other stories about early human migration. We already know our ancestors were wanderers. They walked out of Africa. They crossed deserts. They followed coastlines for thousands of miles. None of that is especially surprising when you think about it, because walking is something legs do. But crossing open ocean is something else entirely. You can't accidentally walk into the sea and end up on an island 25 miles away. The water stops you, or it should. To get from one piece of land to another when there's nothing but deep water in between, you need either extraordinary luck or something that floats and something that steers. And 800,000 years ago, the species we're talking about hadn't even fully evolved into us yet. That gap between what we expect early humans to have been capable of and what the evidence seems to be telling us is exactly where this story lives. And it's a gap that science, despite decades of research, still hasn't fully closed. The key evidence comes from a handful of sites, each one controversial in its own right, each one sitting on top of layers of debate that have kept archaeologists arguing for years. We're talking about places like the island of Flores in Indonesia, where stone tools and fossils have raised questions that nobody has cleanly answered. There are other sites too, scattered across the ancient world, that keep adding threads to a mystery that refuses to unravel neatly. Some researchers look at this evidence and see proof of deliberate seafaring capability far earlier than anyone thought possible. Others look at the exact same data and see alternative explanations, geological quirks, dating errors, possibilities we haven't considered yet. Both sides make compelling arguments. Neither side has definitively won. What science can tell you is that the tools exist, that the dates are genuinely ancient, and that the geography at the time made a water crossing necessary to explain their presence. What science cannot yet tell you is exactly who made the crossing, how, or whether it was a purposeful journey, or something stranger and more chaotic. And honestly, that uncertainty is the most exciting part, because it means the answer is still out there, buried in sediment somewhere, waiting. Before we get into the details, drop a comment right now and tell me where you're listening from and what time it is. Seriously. There's something almost poetic about the fact that you and I are connected across whatever distance separates us while we're talking about ancient humans doing the impossible across open water. Last time I asked, people were tuning in from Cape Town, from Tokyo, from a night shift in São Paulo. I want to know where you are. Because this story is about humanity crossing distances that seemed uncrossable. And in a small way, so is this conversation. So before we go any further, we need to establish something. When we say humans were crossing open ocean 800,000 years ago, we are not talking about you. We are not talking about anyone who looked particularly like you, thought quite like you, or communicated anything like you. The word human is doing a lot of heavy lifting in this story, and it's worth slowing down for a moment to understand exactly what it means at this point in time. Because the answer is complicated in ways that matter enormously to the mystery. The leading candidate for who made this crossing is Homo erectus. And Homo erectus was remarkable. This was a species that first appeared in Africa somewhere around 2 million years ago, and then did something no hominin had ever done before. It left. It spread out of Africa and across Asia, in what paleontologists think was a relatively rapid dispersal, reaching places like Java and China perhaps as early as 1.8 million years ago. By 800,000 years ago, Homo erectus populations had been living across a vast stretch of the Old World for nearly 1 million years. They weren't newcomers. They were established, they were successful, they were by any reasonable measure thriving. But here's where the label gets complicated. Paleoanthropologists do not have the luxury of DNA analysis when they're working with specimens this old. Ancient DNA degrades. In warm, humid environments like Southeast Asia, it disappears almost completely within a few 100,000 years. So the scientists studying early human populations in this region are working from bones, teeth, the occasional fragment of skull, and the stone tools left behind. That's it. And from those fragments they have to reconstruct not just what a creature looked like, but what cognitive category it belongs to. What species, what lineage, how closely related it was to the population 2 valleys over or 2 islands away. This creates a situation where the classification system itself becomes slippery. In the late Pleistocene, across Southeast Asia and the broader region, you had populations that different researchers assigned to different species depending on which features they weight most heavily. Some researchers lump them broadly under Homo erectus. Others see enough variation to split them into separate lineages. There's Homo heidelbergensis in the picture at certain times and places. There are populations that might represent regional variants of erectus, or might represent something in between, transitional forms that don't map cleanly onto any category we currently have. The honest answer is that human species around 800,000 years ago is not a crisp biological label the way it would be today. It's more like a blurry region of the family tree where multiple branches are still close enough to overlap. What we can say with more confidence is the technological baseline. The early human populations in this region were operating within what archaeologists call the Acheulean and related tool traditions. They were making stone tools, sometimes sophisticated ones, hand axes shaped to a consistent design that required planning multiple steps ahead, not just banging rocks together until something sharp fell off. There's evidence of prepared core techniques, where a stone was carefully shaped before the first flake was struck, because the maker already knew what shape they needed the flake to be. That is not instinct. That is forethought. Fire is more contentious. There is evidence from some sites suggesting Homo erectus was using fire, possibly controlling it, possibly transporting embers from natural fires rather than generating their own. But the evidence is patchy and debated, and paleoanthropologists are careful not to project certainty where the data doesn't support it. What the tool record does suggest clearly is that these populations had planning depth, the ability to execute multi-step processes toward a goal that isn't immediately visible. That's a cognitive capacity that separates them from anything that came before. But here's the tension that sits right at the heart of this entire story. Inferring capability from fossils and stone tools is one thing. What a water crossing actually requires is another. Think about what you need to get 20 or 30 people across miles of open ocean. You need something that floats and can carry weight. You need some way to propel it or steer it, because drifting randomly across open water is a death sentence, not a migration strategy. You need enough collective knowledge to attempt it deliberately, or enough extraordinary luck to survive it accidentally. And then, if you arrive, you need a viable founding population, enough individuals to survive, reproduce, and actually establish a presence that leaves stone tools for archaeologists to find 800,000 years later. Every one of those requirements raises its own questions when you apply them to Homo erectus, and paleontologists are genuinely divided about which of those requirements this species could have met. Some researchers look at the sophistication of Acheulean tools and the long-distance planning they imply, and argue that cognitive capacity for something like a raft or a bamboo platform isn't out of the question. Bamboo, which grows abundantly across Southeast Asia, floats exceptionally well and can be lashed into effective platforms without metal or rope. Others look at the same evidence and argue we're making a catastrophic error, reading modern capabilities back into ancient minds just because we want the story to be dramatic. And that tension, that honest scientific disagreement between what the fossils suggest and what a crossing demands, is not going to resolve cleanly. It's going to follow us through this entire story. Because the tools exist, the dates hold up, the geography is unambiguous. But the creature we're asking to have crossed that water is one we only know through fragments. Fragments that can tell us roughly what they ate and roughly how they were built, but cannot tell us what they imagined, what they planned, or what they were capable of daring. That gap between the fossil record and the ocean crossing is where the real mystery lives. And it gets even stranger when you look at the specific island where the evidence was found. The island is Flores. It sits in what geographers call Island Southeast Asia, a sprawling archipelago that stretches from the tip of the Malay Peninsula down through Indonesia and eastward toward the Pacific. Today it's about 360 kilometers long, volcanic, mountainous, green in the wet season, and dry enough to crack the earth in the months without rain. It's home to about 2 million people, and, famously, to the Komodo dragon, which is exactly the kind of detail that makes you feel like this part of the world has always operated by slightly different rules than everywhere else. But the reason Flores matters to this story has nothing to do with what's on it. It has everything to do with what surrounds it. To understand why, you need to know about Wallacea. Alfred Russel Wallace, the naturalist who developed a theory of evolution by natural selection, independently and almost simultaneously with Darwin, noticed something strange about the animals of Southeast Asia in the 1850s. There was a hard line running through the middle of the archipelago. On one side, the fauna looked Asian. Tigers, elephants, rhinoceroses, deer. On the other side, it looked completely different. Marsupials, cockatoos, birds of paradise, species with no connection to mainland Asia whatsoever. This line, now called the Wallace Line, runs between Bali and Lombok, between Borneo and Sulawesi, through a series of deep water channels that have never closed regardless of how dramatically sea levels have fallen. And that last part is the key. Sea levels have changed enormously over the history of our planet. During ice ages, so much water gets locked up in glaciers and ice sheets that global sea levels drop by 100 meters or more. When that happens, shallow continental shelves become dry land. Vast stretches of ocean disappear. Islands merge with mainlands. Land bridges appear where there was open water. This is exactly what happened to the western half of island Southeast Asia. The shallow waters between Borneo, Sumatra, Java, and the Southeast Asian mainland sit on what's called the Sunda Shelf. During the ice ages of the Pleistocene, when sea levels dropped, all of that became dry land. One continuous landmass connecting mainland Asia to what are now islands. Geologists call this region Sundaland. An ancient continent that existed for tens of thousands of years at a time, appeared, disappeared, and reappeared depending on how the climate cycled. Walking from what is now Bangkok to what is now Bali, at the right point in geological history, would have been no different than walking across any other stretch of lowland forest and savanna. No boats required, no water to cross, just land. On the other end of the region, the same thing happened in reverse. Australia and New Guinea also sit on a shared shallow shelf called the Sahul Shelf. During ice ages, they merged into a single landmass, Sahul, a continent that included what is now Papua New Guinea as its northern fringe. Sahul was enormous, ecologically diverse, and critically isolated. Even at maximum sea level drop, there was never a land bridge connecting it to mainland Asia. Deep water channels always remained. Which brings us directly to the problem of Flores. Flores sits in the middle. It is not on the Sunda Shelf. It is not on the Sahul Shelf. It sits in Wallacea, the zone between them, the zone of deep water channels that sea level changes could compress but never close entirely. Even at the lowest sea levels of any ice age on record, reaching Flores from the Asian mainland or from Sunderland required crossing open water. Not once, but multiple times, because Flores is separated from its neighbours by a series of distinct channels, each one a separate crossing, each one a separate problem. The minimum crossings required to reach Flores from the nearest point on Sunderland, even at maximum glacial sea level drop, number somewhere between 3 and 5, depending on which route you take and what the sea levels were doing at the exact moment in question. Some of those crossings would have been relatively short, 2 or 3 kilometres maybe, with the destination visible from the shore. Others would have been longer, with open water stretching to the horizon and no obvious reason to expect land on the other side. This is what makes Flores categorically different from every other early human migration we know about. When Homo erectus walked out of Africa 2 million years ago and spread across Asia, it was walking. When populations reach Java, they almost certainly walk there too, across the exposed Sunda Shelf. Nobody built a boat to get to Java. The ocean did them the favour of retreating. But Flores was different. Flores required the water to actually be crossed, not just waited out. That's the argument that makes paleoanthropologists sit up straighter when someone mentions the Flores evidence. You cannot hand-wave away the geography. You cannot propose a particularly adventurous overland route or a fortuitous exposed shoreline. The deep water channels of Wallacea are a hard constraint, a geological fact that has nothing to do with interpretation or dating method or the biases of the researchers involved. Either something crossed those channels or it didn't, and the evidence from Flores says something did. roughly 800,000 years ago. What that something was exactly we'll get to. But it's worth pausing on the sheer weight of the geographic argument, because it front-loads the mystery in a way that's hard to shake. Most archaeological debates have an escape route. Maybe the dates are slightly off. Maybe the tools were made by a different species than assumed. Maybe there's a stratigraphic contamination issue. The Flores evidence has all of those debates too. But underneath all of them, bedrock, is the fact that the island requires a water crossing. That is not up for debate. And then, decades after the first stone tools were found here, researchers made a second discovery on Flores that reframed the entire question and raised the stakes considerably higher. The island wasn't just evidence of a crossing. It was evidence that whatever crossed had stayed, survived, and done something in the hundreds of thousands of years that followed that no one had predicted and almost no one initially believed. The story starts in a dry riverbed. In the 1950s and 60s, Dutch and then Indonesian geologists working on Flores weren't looking for anything world-changing. They were mapping sediments, tracing old river channels, trying to understand how this volcanic, landslide-prone island had been built layer by layer. In the process, they noticed something odd in a region called the Soa Basin in central Flores. Mixed in with ancient river gravels and volcanic ash were flakes of stone that didn't look like the usual broken rock you get from landslides or natural cracking. They were sharp, angular, repeatedly shaped in ways that suggested intention rather than accident, and they turned up again and again in the same horizons. At first, the finds were just curiosities. Southeast Asia was already known to have Homo erectus on Java by about 1.5 million years ago. So in the early days, the assumption was simple. If there were tools on Flores, they were probably relatively recent, maybe late Pleistocene, made by some population that had wandered over here late in the game. That assumption didn't survive very long. By the 1990s, a team led by Mike Morwood and Indonesian colleagues began systematically excavating in the Soa Basin at a locality called Mata Menge and at nearby sites like Boalesa and Wolosege. They weren't just picking things off the surface anymore. They were opening proper trenches, recording layers, sampling for dating, treating these stones as serious archaeological material rather than strange rocks that might be interesting. What they found at Mata Menge was not subtle. You have a stack of ancient river deposits, sands and gravels laid down by flowing water, capped and interleaved with volcanic tuffs and ash layers from eruptions somewhere up in the island's mountainous spine. Inside one particular set of gravels and fine sediments, associated with fossils of extinct animals, they kept pulling out stone artifacts, core and flake tools. Simple, yes, but consistent. If you've never looked closely at early stone tools, they can all blur together into sharp rocks. But archaeologists are obsessive pattern recognizers. They're trained to tell the difference between a rock that just broke and a rock that's been systematically worked. So what were they actually seeing? The Mata Menge assemblage doesn't contain the big, symmetrical hand axes you might associate with classic Homo erectus sites in Africa or Europe. It's more minimalistic. Think small cobbles and pebbles that have had their edges struck in a controlled way to produce sharp flakes, and the flakes themselves used as cutting edges. You get cores, the parent stones, that show a series of flake scars, each one a negative where a flake was removed. On a natural stone, breaks are random, radiating from impact points like shatter patterns. On a worked core, those scars line up in sequences. There's directionality. You can tell the blows were being aimed. Flakes, sharp-edge pieces removed from those cores. The key features are the bulbs of percussion, little swelling where the hammerstone struck, and platforms where the blow landed. Natural fractures usually don't produce that clean combination of platform, bulb, and ripples radiating out from a single point. Human-made flakes do. Retouched pieces. Some flakes have extra small removals along the edge, turning a generic cutting edge into a more specific scraping or slicing tool. Again, retouch is patterned. You see a consistent angle, a consistent motion. Not the chaotic chipping you get from rocks tumbling in a river. At Matamenga and the nearby sites, all of this shows up in numbers too large and too consistent to be explained by random natural breakage. The raw material isn't just any old stone either. There's evidence of selection. People choosing particular fine-grained rocks that fracture predictably, carrying them some distance, working them in ways that match known early human technologies from elsewhere. That's the threshold archaeologists use for convincing human manufacture. It's not just sharp and it's not just odd. It's repeatable patterns that can't be easily generated by gravity, river transport, or volcanic processes. When those patterns occur in concentrations, in layers, with technological logic behind them, the default explanation is somebody did this on purpose. So far, so good. You have tools. You have them in stratified deposits. You have association with ancient animal fossils, including a dwarf form of the giant stegodon, a kind of prehistoric relative of elephants that seems to have been a Flores specialty. The real shock came when they started dating the layers, because in archaeology, how old is everything? At Matamenga and the Soa Basin, you don't have luxury items like volcanic glass that can be radiocarbon dated. You're way too far back in time for that anyway. Radiocarbon only works reliably to about 50,000 years. The Soa Basin is orders of magnitude older. Instead, researchers turn to methods that anchor sediments in geological time rather than cultural time. One big one is argon-argon dating, a refinement of potassium-argon dating. Volcanic rocks and ash contain minerals with potassium. Over time, radioactive potassium-40 decays to argon-40, a gas. In a closed mineral crystal, that gas is trapped. Measure the ratio of potassium to argon in a volcanic layer, and you can estimate how long it's been since that layer solidified or was deposited. The Soa Basin is layered with these volcanic horizons. If you can date an ash layer below the tools and another above, you can bracket the age of the tool-bearing sediments. At Matamenga, that's exactly what teams did. Argon-argon dates on the relevant horizons put the stone tool layers at around 800,000 years ago, give or take some tens of thousands of years. Other methods help cross-check. Paleomagnetism looks at the magnetic orientation of minerals in the sediments, which record the direction of Earth's magnetic field when they were laid down. Because the planet's magnetic field has flipped numerous times, and the timing of those flips is independently known, you can match the orientation pattern in a sediment stack to the global reversal timeline. The Soa Basin's magnetic signature lines up with an early to mid-Pleistocene age consistent with the argon-argon dates. You also get biostratigraphy, using fossil animals as relative time markers. The presence of certain extinct species, including particular stegodon forms, giant rats, and other island-specialized fauna, points to a time window that again overlaps with the approximately 800,000-year range. When you put it together, the story the geology is telling is stark. The tools at Matamenga and nearby localities aren't late Pleistocene. They're not even mid-Pleistocene in the human sense. They originate in a period when the only hominins we know about anywhere near this part of the world look like Homo erectus in Java, several island hops away. That's when the debate really started. Because if you accept those dates and the human origin of the tools, then you're forced to accept that someone, some human species, was on Flores by around 800,000 years ago. And by the logic of Wallacea, that means they had already crossed multiple deep-water channels. Not everyone was ready to go there. Critics don't usually argue that the stone pieces aren't artifacts at all. The patterns are strong enough that outright denial is a hard sell. The debates focus instead on context and process, on how those stones ended up where they are, and whether the ages assigned to the sediment layers really apply to the tools themselves. One major line of criticism is reworking. Rivers are powerful editors of the geological record. They cut into older layers, scoop up sediments, fossils, even artifacts, and redeposit them downstream in younger beds. Imagine a 500,000-year-old stone tool sitting in a bank, then getting eroded into a river and washed into a 200,000-year-old deposit. If you just dig in that second deposit and date the surrounding sediments, you could mistakenly conclude the tool is only 200,000 years old. The same logic can be flipped. Maybe the Flores tools are much younger than the sediments they're in. Perhaps younger populations left artifacts on some surface, and later erosion dumped those artifacts into cracks or voids inside older formations. mixing time periods together. This is what archaeologists call context mixing. The physical layer you're excavating isn't always a clean, undisturbed package. Burrows, roots, landslides, minor faults, ancient stream channels, they can all churn material in ways that mimic old association. So skeptics of the 800,000 years on Flores scenario ask very specific questions. Are the tool-bearing sediments clearly in place, or are they part of slumped or channelized deposits? Are there signs that the gravels containing tools have been reworked from older or younger layers? Are the volcanic ashes you're dating definitely above and below the exact horizon with the artifacts? Or could there be subtle breaks, missing sections, hidden unconformities? A related criticism focuses on association problems. At Mata Menge, tools, animal bones and sediments co-occur, but that doesn't automatically mean they were all deposited at the same moment. Bones can move within a deposit. Tools can be kicked around by later animals, or even by water after initial burial. If the tools somehow migrated upward or downward into older or younger material, the neat picture of humans here at 800,000 years starts to blur. These are not trivial objections. Everyone working on Flores is painfully aware of them. Papers describing the sites devote long sections to sedimentology, to the structure of the gravels, to microscopic analysis of how grains are oriented, rounded and packed. Teams bring in specialists in fluvial processes and volcanic stratigraphy, specifically to test whether the deposits look primary or reworked. And this is why, despite decades of back and forth, many researchers still take the early presence on Flores very seriously. For one thing, the evidence isn't hanging on a single stone or a single layer. Multiple localities in the Soa Basin show similar tool types in similarly old sediments, tied into the same volcanic and magnetic framework. That repetition across space and layers makes accidental mixing less likely as a complete explanation. For another, the tool technology at these early sites looks surprisingly stable over time. When you compare the approximately 800,000-year-old assemblages from Soa with younger tools on Flores, there's a continuity of approach, a long-lived, simple, core and flake tradition. That kind of cultural persistence fits the idea of a population established on the island, not a one-off accident or a brief visit. Sediment analyses also undercut some of the harshest reworking scenarios. In key layers, grain orientation, sorting and contacts with adjacent strata look like primary river deposits laid down in place, not chaotic jumbles dumped by landslides or later floods. The volcanic ash beds sandwiching them appear in the correct order and are continuous across wide areas, exactly what you'd expect from island-wide eruptions followed by normal erosion and sedimentation. Most importantly, the dates from different methods converge: argon-argon on multiple ash layers, paleomagnetic reversals, biostratigraphy of the animals. They all point toward the same general time window. You can argue about tens of thousands of years at the margins, but it's extremely hard to push the tools down into the comfortably recent past without throwing out a lot of otherwise coherent geology. So the situation looks like this. You have artifacts that meet the criteria for intentional human manufacture. You have them in deposits that, by several independent dating methods, are around 800,000 years old. You have them on an island that could not be reached without multiple open water crossings, no matter what the sea level was doing. You can try to explain away the dates, or the context, or the association, and many people have tried. But with each new season of fieldwork, each new round of analysis, the younger, easier explanations get harder to maintain without inventing increasingly convoluted geological accidents, which leaves you uneasily with the alternative that by around 800,000 years ago, some human species, probably related to Homo erectus, but already taking its own evolutionary path, had not only reached Flores, but stayed there long enough to carve out a durable technological tradition. And then, hundreds of thousands of years later, something happened to that population that nobody was expecting. Because when excavators finally found actual bones on Flores, not just stone tools, they were confronted with a human that looked like it had stepped out of a fantasy story, rather than an anatomy textbook. So at this point, there's a natural objection hanging in the air. If the whole argument about someone crossed deep water 800,000 years ago depends on the age of a few layers in the ground, how sure can we really be that those layers are that old? To answer that, you have to step back and look at the entire dating toolkit scientists are using, not just one number from one lab report. The first tool is the oldest and in some ways the most fundamental, stratigraphy. Stratigraphy is just reading layers. Sediments pile up over time, river gravels, floodplain silts, volcanic ashes, soil horizons. In an undisturbed sequence, the rule is simple. The stuff on the bottom was laid down before the stuff on top. That's called the law of superposition, and it underpins everything. In the Soa Basin, the stone tools sit in a particular set of river deposits. Those deposits are overlain by certain volcanic tuffs and ash beds, and underlain by others. You can trace some of those volcanic horizons for kilometres across the landscape. They don't just show up in one little trench, they're basin-wide sheets. That continuity lets you build a relative timeline. This eruption happened, then these rivers flowed and dropped these gravels with tools, then another eruption blanketed everything. By itself, stratigraphy only tells you older than / younger than. It doesn't give you absolute numbers. To get those, you start layering methods. We already touched on one of the big ones, argon dating. Volcanic materials are your best friends in really deep time because they effectively come with a built-in clock. When a volcano erupts, minerals crystallize from molten rock. Some of those minerals contain potassium. A tiny fraction of potassium atoms are radioactive 40K, which slowly decay into argon-40, a gas. As long as that mineral grain stays closed, no argon sneaking out, no new argon getting in. The ratio of potassium to argon changes at a predictable rate. Measure that ratio today, and using the known decay rate you can calculate how long it's been since the mineral cooled and locked in its argon. Potassium argon, Kr, was the classic method. Argon-argon, Rr, is the more refined version that lets you do internal cross-checks and often yields tighter error bars. On Flores, multiple ash and tuff layers sandwiching the tool-bearing gravels have been dated with AR-AR. They consistently fall in the early to middle Pleistocene range, clustering around that approximately 800,000 year mark. Now add paleomagnetism. When fine sediments settle out in water, or when volcanic ash falls and later gets compacted into rock, some of the iron-bearing minerals inside align like tiny compass needles to Earth's magnetic field at that moment. If you measure the orientation of those minerals later, you can see which way north was pointing when that layer formed. The trick is that Earth's magnetic field doesn't always point the same way. Over geological time, it flips. North becomes south, then back again. These reversals don't happen on a neat schedule, but the sequence of flips is well documented from ocean crust and dated volcanic rocks worldwide. That sequence is called the geomagnetic polarity timescale. So if you go down through a stack of sediments in the Soa Basin, and you see, for example, normal polarity, then a switch to reversed polarity, then normal again, you can try to match that pattern to the global reversal record. When you find a match, you've effectively tagged parts of the sequence with known ages. On Flores, the magnetic signature around the Mata Menge horizons lines up with a period after a major reversal known as the Matuyama-Brunhes boundary, about 780,000 years ago, and before younger events. That's broadly consistent with the RR numbers. Two independent clocks, different physical principles, same ballpark. There are more subtle tools as well. Biostratigraphy, for one. Every period of Earth's history has its own cast of animals. Species appear, evolve, shrink or enlarge, then disappear. If you know that a particular form of stegodon, or a certain giant rat species, only shows up between, say, 900,000 and 700,000 years ago in the region, finding that animal in a deposit instantly narrows your time window. In the Soa Basin, the fossil fauna associated with the tools includes species that match an early Middle Pleistocene age, not something late and comfortable. Again, it's not a precise date, but it's another line of evidence pushing you into that older range. Then there's luminescence dating, used more at some of the younger Flores sites, but conceptually important here. Mineral grains like quartz and feldspar are constantly bombarded by natural background radiation. That radiation knocks electrons into higher energy states where they get trapped in defects in the crystal lattice. As long as the grain sits buried in the dark, those trapped electrons accumulate. Expose the sediment to sunlight or intense heat, and the trap empties. The electrons drop back down, releasing a burst of light, a luminescence signal. In the lab, you can stimulate grains with light or heat and measure how much luminescence they give off. That signal is effectively the time since the grain was last exposed to daylight or heated above a certain temperature. Luminescence works best on younger Pleistocene ages, tens of thousands to a few 100,000 years. But the principle illustrates something crucial. Different methods date different events. Argon dating tells you when a volcanic layer cooled. Paleomagnetism tells you when a sediment's tiny magnetic grains aligned. Luminescence tells you when sand last saw the sun. Fossils tell you when a particular animal was alive. None of these are the age of the stone tool in some direct carved-in-stone way. They're all ages of contexts, and this is where that phrase secure context becomes absolutely critical. When archaeologists say an artifact is in secure context, they mean they're confident that the object hasn't moved significantly since the time the surrounding material formed. The layer is intact. The sedimentary structures make sense. There's no sign of burrowing, slumping, channel cutting, or later disturbances that could have dragged older or younger stuff into the wrong place. Imagine a stone flake resting on an ancient riverbed surface, then getting quickly buried by a quiet flood deposit, then sealed by ash. That's pretty secure. Now imagine a river that thousands of years later cuts down through that old surface, scoops up some of those buried tools, carries them downstream and drops them into a much younger channel fill. If you dig into that younger fill and date the surrounding sediments, you'll get the age of the reworked deposit, not the original moment when the tool was made. Reverse the situation and you can make an artifact look much older than it really is. Younger material collapsing into cracks or voids inside older strata, burrowing animals dragging bones down, roots and soil processes churning things. The whole Flores controversy often boils down to, are the artifacts in a truly primary secure context with those approximately 800,000-year-old sediments, or have they been introduced later into an older package of dirt? This is why field teams obsess over sedimentology. They look at grain size, rounding, how particles are sorted. They examine the boundaries between layers under microscopes. Are gravels imbricated in a consistent direction, like you'd expect from flowing water, or jumbled in a chaotic mass? Are ash beds continuous and flat, or chopped up and folded? Are there burrows, root traces, microfaults? If you see undisturbed, horizontally bedded river gravels with normal sorting capped sharply by a pristine traceable ash, and your tools are distributed within that gravel but not smeared across multiple layers, that supports a secure context. If instead you find clasts from different ages mixed together, lenses of material cutting into older units, or artifacts hugging the walls of ancient cracks, alarm bells go off. Now, even when you're convinced the context is good, there's still the question of uncertainty. Dating methods always come with error bars. An RR date might come back as 820,000 years plus or minus 40,000. That means the true age within a certain confidence level lies somewhere between 780,000 and 860,000 years. Paleomagnetic correlations can have their own wiggle room, especially near reversal boundaries. Biostratigraphic ranges can be broad. A species might have persisted for 300,000 years. Normally, those tens of thousands of years don't change the big picture. Whether the tools are 790,000 or 830,000 years old, you're still talking about a very ancient occupation by early humans. But when you're asking specific questions like, did these hominins cross a deep water channel before a particular sea level low stand? Or were they there before or after a certain climate event? Small shifts matter. For example, imagine a scenario where one model of sea level change suggests a series of especially extreme low stands around 900,000 years ago, with slightly higher but still low stands around 800,000 years ago. If your dates for a site are crude, you might argue the crossing happened during some best-case window when islands were maximally close. Tightening the dates by even 50,000 years might move your occupation into or out of that hypothesized window. Suddenly, instead of they probably rode a rare combination of currents and super low sea level, you might have to accept they crossed when conditions were only marginally favourable, implying more capable seafaring or more deliberate planning. Or consider Flores itself. If you could somehow show that the earliest tools weren't 800,000 years old, but say 500,000, you'd instantly make the story less radical. You'd be placing open water crossings closer to the time when we already know other hominins were doing sophisticated things elsewhere. That's why some critics are so keen to argue for reworking and younger ages. It doesn't just change a number, it relaxes the implications. On the flip side, if new work nudged the ages older, toward 900,000 or even 1,000,000 years, it would push the technological and cognitive requirements further back into a time when the only likely candidates are very early Homo erectus-like populations. The older it is, the more it stretches our models of what those hominins could do. So where does the consensus actually sit right now? Most researchers who've worked directly on the Soa Basin agree on a few broad points. First, the volcanic and magnetic framework is early to middle Pleistocene. The ash layers really are that old. You'd have to throw out a lot of well-understood geochronology to make them say 200,000-year-old events. That's not a move many geologists are willing to make. Second, the tool-bearing gravels occupy a consistent stratigraphic position between those dated horizons. You can debate fine details of their formation, but they're not obviously some late intrusive feature sitting in a crack. Third, the associated fauna match that general age. They don't look like late Pleistocene assemblages. What remains contested is the exact tightness of the association. Are all the artifacts truly primary to those gravels? Could a fraction of them have been introduced later? How clean is the sequence at every single site? Do all the localities tell the same story, or are some more secure than others? And crucially, what that age implies about behaviour. If you accept that some hominin population was on Flores by roughly 800,000 years ago, you're accepting that they crossed real ocean barriers, not just shallow tidal flats, not just swampy channels you could wade at low tide. Actual open water, deep enough that even at the lowest sea levels there were no land bridges. If you don't like that implication, you can lean on the remaining uncertainties in the dating and the context and hope that future work will pull everything into a more comfortable range. So far, though, each new round of analysis has tended to reinforce the broad approximately 800,000-year time frame rather than demolish it. The error bars might shift a bit. Individual sites might get revised. But the basic picture, early tools in very old sediments on a very isolated island, has held up, which leaves us with an uncomfortable but increasingly plausible scenario, that by about 800,000 years ago some human species wasn't just making stone tools in river valleys. They were already doing something our textbooks long insisted came much later. They were dealing with the ocean. To understand just how big a deal that is, you have to look at what those ocean barriers around Flores actually looked like, even at the lowest possible sea levels, and why you can't make them disappear just by tweaking a few dates. When people hear sea level was lower, they often imagine the map just gently zooming out. A bit more beach, a wider continental shelf, maybe some extra sandbars. In a lot of places that's not totally wrong, but in Wallacea, the jigsaw of islands between mainland Southeast Asia and Australia, it's the wrong mental picture. Lowering the sea doesn't turn Wallacea into a solid land bridge. It turns two already huge land masses into even bigger ones, and leaves a chain of deep, stubborn channels between them. On the west you have Sunda, the combined shelf of what's now Thailand, Malaysia, Borneo, Java, Sumatra. On the east, Sahul, Australia, plus New Guinea and Tasmania, all fused together when the oceans dropped. Wallacea is the broken middle, A scattering of islands, Flores, Timor, Sulawesi, Halmahera, and more, that never fully connect to either side, no matter how far you crank down the water. The reason is simple and brutal: bathymetry, the depth of the seafloor. Some parts of the Sundershelf are only a few tens of meters deep, drop sea level by 120 meters, like during the coldest glacial stages, and they pop up as dry land. But in the straits around Flores, the seafloor doesn't sit at -50 or -80. It plunges to hundreds, even thousands of meters deep. Those are basins, not puddles. You don't drain them with Pleistocene climate change. Oceanographers and paleogeographers have mapped this out in detail. Even at extreme low stands, there are still key deep water gaps, persistent barriers you cannot turn off. The Lombok Strait between Bali and Lombok is one. Today it's roughly 35 kilometers across at its narrowest and more than 300 meters deep in the channel. Even if you subtract a full 120 meters of sea level, you still have a deep, wide stretch of open water. East of that, the Alas and Sape Straits, carving separations between Lombok, Sumbawa and Komodo. They too sit over steep, deep channels. Then, crucially for our story, the straits around Flores itself. The Flores Sea to the north, the Sumba Strait to the south, various passages tying into the Banda Sea. Depths again plunge into the hundreds or thousands of meters. Flores is not sitting on a gentle shelf you can just walk to when the tide goes out. It's ringed by blue water. Paleogeographic reconstructions for glacial maxima show that yes, the coastlines of these islands would have advanced. Exposed shelves would make some distances a bit shorter. Bali, Lombok and Sumbawa would have been fatter. Some tiny islets would have merged into larger islands. But the crucial thing never happens. There is never a solid land bridge from Sunda to Flores, or from Flores onward towards Sahel. The Wallace Line, Alfred Russel Wallace's famous biogeographic boundary marking a sharp change in animal and plant life, reflects that reality. It's built on deep channels that even an ice age can't erase. Now, add time. The Pleistocene wasn't one long static low sea level. It was a roller coaster. Ice ages came and went. Glaciers grew, sea level dropped. Glaciers melted, sea level rose. Over the last million years, global sea level swung up and down by over 100 meters multiple times. During colder phases, more water was locked up in ice sheets on land, so coastlines worldwide shifted outward. During interglacials, warmer intervals like today, ice shrank and seas flooded continental shelves. That means any hominin population trying to move through Wallacea over many tens of thousands of years would not have seen a single fixed geography. Islands would wax and wane. Distances between them would lengthen and shorten. But here's the catch. Those deep troughs around Flores don't care. At a high stand like the present, you might be looking at, say, 25 or 40 kilometers of open water between one island and the next. At a low stand, that might shrink to 15 or 20 kilometers, depending on local topography. Maybe new islets appear, making a crossing a bit more stepwise. Maybe a shallow bank becomes a reef platform that occasionally breaks the surface. But we're not talking about walk across at low tide distances. We're talking about horizons. Even in the most favourable Pleistocene scenarios, at least some of the crossings into and within Wallacea would always have been genuine blue water gaps. Distances far beyond the swimming ability of any ape, with no land in sight from the departure shore. So any model that tries to sneak humans into Flores by saying, well, sea level was lower, runs into the same brick wall. Lower sea levels change the shape of the problem, but they don't remove it. That's just the static picture. Once you put the ocean in motion, things get even more interesting. Wallacea sits where major current systems collide and squeeze through narrow passages. Today, one of the key players is the Indonesian through-flow, the stream of warm surface water that moves from the Pacific into the Indian Ocean through this very maze of islands and straits. It's not a gentle drift. In places like the Lombok Strait, measured surface currents can run several knots with complex eddies and tidal flows on top. Those currents are not random. They're shaped by the difference in sea level between the Pacific and Indian Oceans, by the monsoon system, by the position of the equatorial current belts. During the Pleistocene, the exact patterns would have shifted as climate oscillated, shorelines moved and wind belts migrated north or south. But what we can say with confidence is that strong directional currents would still have been there. Narrow straits tend to focus flow, not calm it. Then you have the winds. Modern Wallacea is under the sway of the monsoon. Seasonal wind reversals dominate, roughly one part of the year with winds blowing predominantly from the northwest, another with winds from the southeast, plus the trade winds on broader scales. The details shift from year to year, but the pattern is robust. Paleoclimate data, things like ocean sediment cores, isotope records and dust deposits, suggest that monsoon systems were present and active throughout much of the Pleistocene, though their strength and exact timing varied with global ice volume and orbital cycles. So our early seafarers, if that's what they were, would have been facing a world where, depending on the season, the wind could help them, fight them, or push them sideways into places they never intended to go. Combine strong, sometimes opposing winds with narrow, deep straits and powerful currents, and you don't get a placid lake. You get a dynamic, sometimes dangerous seascape. Rafts or simple watercraft out in those channels would not simply drift aimlessly. They'd be carried along preferred paths, accelerated in some bottlenecks, perhaps trapped in eddies elsewhere. Now imagine trying to move across this watery labyrinth not in one enormous leap, but in stages. One way to soften the mental shock of 800,000-year-old humans crossing open ocean is to picture it not as a direct Bali to Flores sprint, but as a series of stepping stone hops, and there is some plausibility to that. As sea level drops, islands grow and multiply. Small patches of high ground that are submerged today might have been low, scrub-covered islands back then. Modern bathymetric maps show seamounts and submarine ridges that come within a few tens of meters of the surface. Expose those and you get specks of land, maybe too small to support a permanent population, but big enough to land on, rest, gather shellfish, and wait for better weather. So a hominin group might have moved from the Sunda Shelf out to one island, then, generations later, from that island to the next. Over thousands of years, you can traverse considerable distances with a technology and planning horizon that, in each individual step, doesn't look impossibly advanced. But that only goes so far. The critical point is that no sequence of stepping stones completely removes the need for at least one substantial deep water leg. Somewhere along any plausible route into the heart of Wallacea, you run out of half measures. There is always at least one channel where you cannot see the far shore from the near one at Pleistocene sea levels. There is always at least one crossing where, once you push off, you are committed to hours, maybe a day or more, of being at the mercy of wind and water with no guarantee of what lies ahead. That's where the distinction between accidental drift and intentional voyaging becomes unavoidable. Accidental drift is the minimalist explanation. It doesn't require navigation, planning, or a concept of island out there beyond the horizon. You just need bad luck and buoyancy. People get swept out to sea on natural rafts of vegetation during floods. Storm surges can rip up whole riverbanks and carry trees, soil, and anything clinging to them far offshore. In that scenario, small groups of hominins might have ended up on floating debris, blown or carried across a strait by wind and current, and deposited, half dead, on a new island. Intentional voyaging is different. It implies that someone decided to leave, that they built or modified something to float, loaded it with people and maybe supplies, and pushed out knowing, or at least strongly suspecting, that there was land to aim for. It implies some understanding of wind and current patterns, some cultural memory of, if you follow the swell in that direction at that time of year, you might find something. Can we rule out accidental drift for Flores? Not really. Deep time doesn't come with eyewitness accounts. In a world of storms, tsunamis, and unstable coastlines, rare but catastrophic events absolutely happen. Given enough thousands of years, a few such rafts could, by pure chance, cross even very challenging channels. But if you lean entirely on accident, you run into problems. One storm-tossed family landing on an empty island is not a guaranteed population founder event. They might all be men. They might be too few to maintain genetic and cultural viability. They might simply die. To explain a long-lasting evolving population, you usually need repeated arrivals, or at least one arrival big enough and lucky enough to take root. Repeated accidents start to blur into something else. If hominins keep getting washed into the same general direction, generation after generation, they're going to notice. They'll see driftwood and pumice and carcasses appearing from certain quarters. They'll associate certain winds or swells with things coming from out there. At some point, curiosity and opportunism could push them from passive victims of drift toward active exploitation of that pattern, hanging onto rafts on purpose, pushing off ahead of the storm, maybe even nudging logs together to make something more stable. Intentional voyaging, on the other hand, demands more from our mental model of these early humans, but solves some demographic and geographic puzzles. If they could choose when to leave, choose who went, and roughly where to aim, you don't need improbably many freak storms to seed an island. A handful of deliberate crossings over a few thousand years would be enough. Where does Flores sit on that spectrum? That's the unresolved core of the mystery. The geology of Wallacea tells us that, by about 800,000 years ago, no realistic combination of sea level lowstands and stepping stone islands can erase all the deep channels. Anyone who made it to Flores had to get past real ocean, with real currents and seasonal winds, in at least one leg of their journey. The physics of the region tells us those journeys would have been shaped by powerful, often predictable flows and wind regimes. Forces that can carry helpless drifters, but that can also be learned, exploited, and eventually mastered. Whether the hominins who first reached Flores did so clinging to storm-torn vegetation by sheer accident, or on the first crude, deliberately made craft aimed into a known current, is something the stones and bones can't yet tell us. What they can tell us is that one way or another, those ancient humans crossed a line that even an ice age couldn't move. And once you appreciate just how stubborn those ocean barriers are, the next question becomes unavoidable. What kind of watercraft could a species 800,000 years ago possibly have had? And why haven't we found a trace of it? If you go looking for the first boat in the archaeological record, you're going to be disappointed. Wood, fibre, bark, reeds, vines, bamboo, the stuff you'd actually build a simple craft out of, does not like to hang around for 800,000 years. It barely likes to hang around for 8,000. What we do find, even in relatively recent prehistory, are ghosts, indirect traces, things that only make sense if boats, or something boat-like, already existed. In Europe, the oldest actual dugout canoes we've found are on the order of 10,000 years old. In places like the Netherlands and Denmark, they survive because they were rapidly buried in waterlogged mud and peat, under anaerobic conditions that slow decay. Even then, they're rare. For earlier periods, the evidence is mostly circumstantial. Obsidian from one island showing up on another, animal bones from species that never lived on that shore, fish that live far offshore suddenly becoming a big chunk of someone's diet. Move back to the timescales we're talking about, hundreds of thousands of years, and those fragile traces are almost guaranteed to be gone. Coastlines have moved tens of kilometres. Whole continental shelves that would have been the prime real estate for early beach camps and launch sites are now drowned under 50 or 100 metres of water. Any logs, rafts or lashings they left behind have long since rotted, been eaten or been ground to nothing by waves and sediment. So when you hear we have no boats from 800,000 years ago, that's not a shocking discovery. That's exactly what you'd predict from basic taphonomy, the study of how things decay and fossilize. Heavy, mineral-rich bones and stones sometimes make it. Soft organic materials almost never do, unless they get entombed in some kind of preservational jackpot, a cave with perfect conditions, a frozen bog, a desert tomb. Early watercraft lived and died on dynamic shorelines and open beaches, the worst place if you want something to become a fossil. What archaeologists look for instead are patterns that scream somebody was crossing water, even if all the wood is gone. On Flores, that's the stone tools themselves and the sheer age of the sediments therein. The tools match the mainland technological traditions closely enough that they look like part of the same broader culture, not a totally separate invention, but they're on an island you can't walk to. Something carried that culture, and those genes, across the water. So what could that something have been? Strip away our modern image of ships and sails and you very quickly get down to basics. You don't need a Viking longship to cross 15 or 20 kilometres of water. You need flotation, stability, and a way to push or steer. The most minimal option is not even really a boat in our sense. It's a natural float. A big log or a tangled mat of roots and vegetation ripped off a riverbank in a flood. We know from modern disasters that such rafts can stay afloat for days or weeks, especially if they're loaded with soil and plants that keep them buoyant. An unlucky, or lucky depending on your perspective, group of hominins could end up stranded on one of these, clinging to branches while wind and current do the navigating. But once a species has even a little bit of technological know-how, there's an obvious next step. You stop waiting for a perfect storm to build the raft for you. You modify what the river and forest give you. Take logs. One log is tippy. 2 logs, roughly parallel and more stable. Tie 3 or 4 together, and suddenly you have a platform you can stand or sit on, without flipping into the water every second. That is a raft. To build it, you need almost nothing that we would recognize as complex technology. You need to know how to bind things together, which is a skill we already know very early hominins had. That binding could be as simple as twisted vines, strips of bark, or long grass. If you've ever tried to break living vine in a forest, you know it's incredibly tough. Early humans were already using plant fibers for things like tying stone tools to wooden handles hundreds of thousands of years later. The basic insight that long, flexible plants can be braided or twisted to hold other objects probably goes back far earlier. You don't leave fossils when you do this. You leave habits. Then there's bamboo. In much of island Southeast Asia, including areas around Wallacea, bamboo is abundant. It's practically nature's boat kit. Hollow, sealed segments trap air and float extremely well. Split it, and you get planks and slats. Bundle and tack comes together and you have an incredibly buoyant raft, lighter and easier to maneuver than one made of dense hardwood. You don't even have to cut down large trees. You can gather what storms and landslides already bring down. Simple rafts like this don't require metal. They don't require sails or complex joinery, but they do require a suite of skills that, taken together, are not trivial. You need to understand binding, how tight to tie, what plants won't snap when wet, how to lay a log so the raft doesn't twist apart in choppy water. You need a sense of balance. Moving around on a floating platform is different from walking on land. People have to learn where to sit, how to distribute weight, when to stay low. One person could manage that by trial and error. A group has to coordinate who sits where, who paddles, who keeps watch. You need propulsion, paddling or poling. For near-shore travel in shallow water, a simple pole works, a straight branch, stripped of side twigs, long enough to reach the bottom. Push against the seabed or riverbed, and you move. In deeper channels, you need something that can bite into water itself. That's where paddles come in. Broader ends on a stick. They can be carved crudely with stone tools. A flat-bladed paddle is essentially a large elongated scraper on a handle, the kind of thing a Julian-level stone technology is perfectly capable of roughing out. You also need loading skills. Put too many people or heavy stones on one edge of a raft and you flip. Stack goods in the middle, tie them down, maybe wedge them between cross pieces, and you create a centre of gravity that makes the craft more forgiving. These are intuitions you develop quickly if your life depends on not capsizing in rough water. And behind all of that, there's planning. To build even a very crude raft, you have to anticipate a future situation. We will be on the water. We will need this thing to float. We will need food and tools once we land. That means collecting materials ahead of time, not just grabbing whatever is at your feet when you decide to go. It means caching wood, stripping bark, setting aside vines to dry or soak so they're easier to work. Here's where fire and cutting tools come in. A stone hand axe or large flake turns the forest into a toolbox. With no cutting tools, you're limited to what you can break or tear off by hand. With sharp stone, you can fell small trees, trim branches, shape ends so they fit together better. You can even rough out something like a dugout canoe by chipping and burning. Controlled fire magnifies this dramatically. Fire-hardened wood is more resistant to rot and abrasion. Fire can hollow a log that's too thick to dig out with stone alone. Burn, scrape, burn, scrape, over and over. That technique is documented ethnographically in many later cultures and doesn't demand metallurgical tools, only patience and an understanding that fire can be tamed, not just feared. Fire also lets you transform plant resins into primitive glue or pitch. Heated sap from certain trees becomes sticky and water-resistant. Combined with fibres and wedges, that can improve the joints in a raft or the seal in a hollowed log. Again, we have direct archaeological evidence of people using plant resins as adhesives much later in the Pleistocene. The cognitive prerequisites, noticing that heated sap changes properties, experimenting with it, applying it to practical problems, are rooted in the same curiosity that drives toolmaking in general. Put all of this together, and you get a picture of early watercraft that is both humble and powerful. No masts, no metal nails, no carved figureheads, just logs and bamboo, vines and fire, muscle and memory. And because it's humble, because it's made from exactly the kind of biodegradable materials that nature recycles with ruthless efficiency, it vanishes almost without a trace. Think about what would need to happen for an 800,000-year-old raft to survive for us to find. It would have to sink or be abandoned in just the right environment, quickly buried in low-oxygen mud, protected from waves, bacteria and burrowing animals. The coastline it sat on would have to avoid being eroded away, drowned or uplifted and scoured. Then, in the last geological eye blink, that exact spot would have to be cut by a river or quarry or road project, and an archaeologist would have to be there at the right moment to notice a strange pattern of decayed wood stains in the sediment. Any one of those steps failing means the craft is gone, and that's assuming the craft ever sat still long enough to be buried at all, rather than being smashed by waves or eaten by shipworms. That's why, in deep time, we are forced to work mostly with negative space. We reconstruct what must have been there from what is left around it. Stone tools stranded on impossible islands, faunas that make no sense without human transport, genetic signatures of isolated populations where you'd otherwise expect continuity. So when we say, we have no direct evidence of boats 800,000 years ago, that's not a mic drop against ancient seafaring. It's a statement about the brutality of the fossil record. The absence is exactly where you'd expect it, even in a world where simple rafts and log craft were being used routinely. The more interesting question isn't, why haven't we found their boats? It's, given that we probably never will, how can we tell whether those crossings were desperate one-off accidents or the first glimmers of intentional voyaging? To answer that, we have to leave the missing wood behind and look instead at patterns of arrival, population size and timing. One accidental raft might seed an island by sheer blind luck. Building and launching craft on purpose with chosen crews and supplies could do something much more profound. Turn a single, terrifying crossing into a repeatable strategy. And that's where the debate over Flores leads next. Were those early hominins just victims of storms, or were they already beginning to think like sailors? Let's start with the simplest story. You're on a mainland coast 800,000 years ago. Life is already dangerous. Rivers flood, forests burn, storms rip entire sections of shoreline into the sea. Sometimes that chaos builds its own vehicles. Modern ecologists have watched this happen. After big floods or tsunamis, you sometimes get what they call vegetated rafts. Huge tangled mats of soil, roots, tree trunks, shrubs, and whatever else the riverbank was holding together. Some are the size of a bedroom, some are the size of a house. They can carry insects, reptiles, small mammals, even in principle a few unlucky primates. The accidental drift hypothesis says that's all you need. A storm tears away a piece of forest where a group of hominins is foraging or sheltering. A riverbank collapses with people on it. A tsunami surges inland, then sucks back out, taking vegetation, carcasses, and surprise survivors with it. They don't choose to launch. They're just suddenly not on land anymore. If this sounds far-fetched, remember that we see modern analogues. After the 2011 Tohoku earthquake and tsunami in Japan, debris rafts, entire dock sections, chunks of buildings, drifted across the Pacific and landed in North America years later, still carrying living organisms. after major floods in the Amazon. Whole tangles of trees break off and float for weeks, full of insects, frogs, even monkeys. Scale that down to a shorter island-sized crossing. Take a vegetated mat ripped from some ancient river delta in what's now Southeast Asia. Let the prevailing winds and currents push it out into a narrow strait. Somewhere on that raft, clinging to branches and mud, are a handful of hominins who woke up that morning thinking they would collect shellfish and tubers like any other day. On this account, Flores and other deep-water islands don't require sailors. They just require victims of bad weather who got pushed by physics into a place they never meant to go. The appeal of this is obvious. It doesn't ask early humans to invent anything. No raft planned, no paddles carved, no let's see what's over that horizon, conversations around the fire. Just the existing natural world, plus the occasional catastrophe. The problem comes when you start doing the math on survival. To establish a population on an island, you need more than one traumatized survivor washing up on a beach. You need a breeding group. Not necessarily a huge one. In theory, even a very small founding population can grow if conditions are good. But more than a lone starving castaway. So picture a vegetated raft a few tens of meters across. How many hominins does it plausibly carry? Maybe a small band sheltering in a grove that collapses together. 10, 20. If you're very generous, 30 or 40. Now make a list of everything they need to make it alive across 15 or 20 kilometers of open water. Fresh water, food, shade, some way to avoid being swept off by waves. Time. Even if the crossing only takes a couple of days, exposure is brutal. The equatorial sun cooks bare skin. Salt spray dehydrates you faster than you think. You can't hunt. You can't gather anything that isn't growing on your accidental island. If the raft is mostly clean logs and roots, you might be out of drinkable water within hours. You can model this in simple terms. Take a small group with no preparation, no deliberate provisioning, and no idea where they're going. Assume half of them are injured by the initial event, crushed under falling trees, battered by waves. Assume some are children or older adults. Survival rates plummet fast. And then there's the landing problem. A vegetated raft doesn't aim itself. It follows wind and current. For a storm-torn group on the Sunda Shelf, most possible directions lead them along coasts or back onto continental shorelines. Only a narrow cone, in space and time, flushes them through a gap and onto the tiny target of a specific island. The number of things that have to go right is impressive. The raft has to hold together. The current has to flow toward the island, not away. Winds can't drive the whole thing sideways into some dead-end bay. The crossing has to be short enough that at least a few reproductively viable individuals are still alive when it hits shore. Run that as a mental simulation, and it's hard not to feel the odds collapsing. Not to zero. Nature has a long time to roll the dice, but to the point where each successful colonization looks like a once-in-a-million-years fluke, and that, defenders of the accidental model will say, is fine. We have millions of years. Rare events happen, but now flip to the other side of the argument. Instead of picturing your ancestors as disaster victims, imagine them as experimenters. On a familiar river mouth, groups of hominins are already using logs as toys and tools. Kids cling to driftwood and kick in the shallows. Adults figure out they can cross a small channel faster by floating than by wading. Someone lashes 2 logs together with vines. It works better. That experience sticks. For a long time this is local. They cross rivers, lagoons, protected inlets. Distances are short. If something goes wrong, they're never more than a few hundred meters from shore. But every successful short crossing builds skill and confidence. They learn, without writing anything down, a body of rules. How many people a given raft can hold, how to angle into waves, how to push off from rocks without snapping the craft in half. Who in the group has the best balance and reflexes? Add in the social layer. Early humans didn't just sit still when times were bad. They ranged widely. They explored new patches of forest, new river valleys, new coastlines. Maybe they follow a line of islands you can see from the beach, low silhouettes on the horizon that look tantalizingly close. Maybe groups on one headland can see smoke from another headland across the strait, and at some point someone thinks, we can get there. Intentional crossing models don't imagine the first group to Flores waking up one morning and deciding to sail directly into unknown blue water. They imagine a learning curve. You start with tiny hops, across river branches to sandbars, to near-shore islets you can still swim back from. Some attempts fail, people drown, rafts flip. Those failures teach caution and technique. Over generations, the safe distance grows. A crossing that was once unthinkable becomes routine. The knowledge is social. Elders scold reckless youngsters. Skilled raft makers get status. Stories accumulate about near misses and successful landings. Now give that process hundreds or thousands of years in a region full of channels and islands. Intentionalists argue that at some point the line between river and sea stops mattering. If you can manage 3 kilometers of open water, 5 is not a new universe. If you can keep a raft intact for an afternoon, you can push into gaps between land masses that were once unreachable. Crucially, these trips aren't blind. Groups that have already seen an island on the horizon know that land is out there. They can set off on days when wind and swell are right. They can load the raft with skins full of water, shellfish, tubers, maybe even burning embers in a bark container to restart fire when they land. They also have the numbers advantage. If you choose who gets on the raft, you can bias the crew toward young adults and adolescents, the demographic most likely to found a new population. In this picture, colonizing Flores is still dangerous, still high stakes, but not a freak accident. It's the endpoint of a long series of deliberate small-scale experiments in water crossing. So how would we tell which story is closer to the truth? With archaeology, we can't interview the people involved. We can't read their logs. All we get are layers of sediment and whatever's trapped in them. Under an accidental drift scenario, you expect colonization to look like a single, rare spike. The earliest tools on an island might appear abruptly, then perhaps vanish for a while as that tiny, fragile population struggles to establish itself. The stone technology might look like a random sample of what existed on the mainland, with no clear signs of specialized seafaring culture. If the founding event was a desperate storm raft, the people who arrived weren't necessarily the most technically skilled or representative of their source population. They were just the ones in the wrong place at the wrong time. You might also expect long gaps between early occupation and any sign of more intensive use. One freak arrival 800,000 years ago, then very little, then maybe a second wave hundreds of thousands of years later, when more advanced hominins arrive with better tools and more predictable methods. Under an intentional crossing model, the archaeological record starts to look different. Repeated voyaging, even with crude rafts, means more people arrive over a shorter window of time. That boosts the chance that a sustainable population establishes quickly. You might see a relatively rapid build-up of sites and artifacts after the first appearance. Tools at multiple locations, not just one lucky landing spot. The technology might track mainland developments closely, because contact isn't a one-off. Even if most trips are one-directional and risky, some gene flow and idea flow continues. Intentional travel also changes how people use the island. If you've chosen to go there, perhaps because you know there's game or fresh water, you're more likely to exploit it systematically. You could see more intense butchery sites, repeated occupation of the same shelters, and eventually evidence that the population is adapting locally, changing tool forms, hunting strategies, maybe even body size, while still bearing the imprint of a continuing connection with the wider region. The frustrating truth is that, with the data we have now, Flores can be argued either way. The tools are old and clearly not the result of a fleeting stopover. Whoever got there stayed for a long time. That persistence feels more compatible with some degree of intentionality, of groups continuing to arrive, replenishing and reinforcing the population. But the earliest arrival could still have been an accident. One big, improbable raft event might have seeded a small founding group. Once established, that population could have grown and diversified without any further contact. Later hominins could then have developed local watercraft skills independently, turning a single stroke of luck into a long-term presence. Part of why the debate refuses to die is that both models can be made to sound plausible, and both can hide behind the brutal limits of the record. We don't have fine-grained, continuous sequences of artifacts showing a clear ramp-up in maritime skill. We don't have DNA from those earliest islanders to tell us whether they were the product of a tiny founder group or multiple waves of migrants. We're reconstructing behaviour from a scatter of stones and a few scattered bones, and human imagination cuts both ways. On one hand, it's easy to underestimate early hominins, to assume they were incapable of planning, curiosity-driven exploration, or technological tinkering. On the other, it's just as easy to project our own adventurous, exploratory impulses backward in time and see sailors where there were only castaways. So archaeologists argue. Some emphasize the power of rare events over deep time. Others lean into the emerging picture of early humans and their relatives as relentless experimenters, constantly pushing the edges of what their tools and brains could do. Until we find something more decisive, a clearer pattern of occupations, a series of dated sites that show whether colonization was abrupt or gradual, accident or intention, stays an open question. But whichever side you lean toward, the implications are huge. If Flores was settled purely by drift, it tells us the world can reshuffle species in ways that no one involved ever planned. If it was settled by design, even in the most primitive way, it means some human species were thinking in terms of crossing horizons hundreds of thousands of years earlier than most people realize. To see how later evidence tilts the scales, we have to fast forward in time to a period when we finally get a clearer glimpse of deliberate seafaring. Fast forward to a much more familiar cast of characters, our own species. By about 50,000 to 45,000 years ago, Homo sapiens are turning up in places that absolutely, unquestionably require crossing serious stretches of open water. Australia, New Guinea, the Bismarck Archipelago, eventually islands all the way out into remote Oceania. There is no way to walk there, no seasonal land bridge, to get from Sunda, the Pleistocene landmass that joined mainland Southeast Asia, to Borneo, Java and Sumatra, to Sahul, the supercontinent made of Australia, New Guinea and Tasmania. You have to cross multiple deep-water gaps. Even at the coldest ice ages, when sea levels drop more than 100 metres, those gaps stay ocean, and somehow people still got across. Archaeologists generally agree that the first humans reached Australia at least 50,000 years ago, maybe earlier. To do that, they had to island hop through what's now Indonesia and eastern Wallacea. Timor, the Aru Islands, may be Flores' neighbours. Some of the jumps are small, a couple of kilometres, sometimes less, but a few are on the order of 20, 30, even 80 kilometres of continuous blue water, depending on the exact routes and sea level curves you use. You don't drift 80 kilometres to Australia on a random clump of vegetation, not with a viable founding population, not in a way that leaves widespread archaeological signatures across a continent within a relatively tight window of time. So for Homo sapiens, by this late date, deliberate voyaging is almost inescapable. People were building something that could be paddled or poled. They were loading it on purpose. They were pointing it at land they couldn't always see. This is where the temptation comes in. If our species could do this 50,000 years ago, isn't it natural to assume earlier humans were doing something similar 800,000 years ago, just with cruder gear? Maybe. But we have to be careful about what this precedent really shows. First, strip away some romantic assumptions about what seafaring requires. When you imagine the first Australians, you might picture boats carved with animal heads, guided by navigators memorizing star paths, chanting myths about ancestral voyages. That's not what the evidence demands. To cross 20 or 30 kilometres of water, in good conditions, you don't need elaborate symbolic culture or high ritual. You don't even need language as complex as ours today, though it likely existed by then. You need something much more basic. A buoyant platform that doesn't immediately fall apart, a minimal sense of direction, and the decision to put multiple people on it at once. Modern hunter-gatherers show us that relatively simple watercraft can be both effective and technologically humble. Dugout canoes created with stone tools, bundles of reeds tied with plant fibres, logs lashed together into rafts. None of this needs writing, compasses, or abstract geometry. It needs trial and error, social learning, and enough communication to say, not like that, like this. And when you look closely at the earliest evidence for people in Sahel, that's basically what the models assume. Not fleets of sophisticated ships, but repeated short-range crossings with simple rafts, canoes, or log bundles, probably hugging lines of sight between islands whenever possible. In fact, some of the strongest arguments for deliberate voyaging don't come from the style of boats at all. They come from the numbers. If you want a new continent to fill up with people quickly, you can't dribble in one castaway every 1,000 years and hope for the best. You need groups big enough and crossings frequent enough that populations grow instead of just blinking out. Genetic models and archaeological estimates of early Sahel colonization suggest founding groups on the order of dozens to hundreds of people, not single families. That doesn't mean 100 people all got on one giant raft. It could mean multiple small parties arriving in a reasonably short span of time, decades or centuries instead of tens of thousands of years. Whatever the exact scenario, the math points in a similar direction. Once Homo sapiens start showing up on deep-water islands, they do it in a way that looks intentional and somewhat organized. People are not randomly falling into boats and hoping for the best. They're using water as a planned route. From that, we can cautiously extract a few lessons that might help us think about Flores 800,000 years earlier. Lesson 1. You don't need full-blown modern culture to end up on islands. The early Australians probably had rich symbolic lives. They painted, carved, and told stories that we only glimpse through rock art and ethnography. But their watercraft themselves didn't have to be products of that symbolic world. A log raft works whether or not you've invented mythic sea gods. Rafting is a physical problem: float, balance, propulsion, timing. So if Homo sapiens with relatively simple rafts could cross 20+ kilometers of open water, it's at least plausible that earlier humans with decent cognitive abilities could manage 10 or 15, under good conditions, given enough time to learn. Lesson 2. Minimal viable group size matters more than we might think. Later island colonizations give us a rough sense of how many people it takes to establish a population that doesn't immediately inbreed itself into oblivion. Geneticists modeling founder effects in island populations, including some in the Pacific, repeatedly bump into the same ballpark. A founding population of maybe 20 to 50 individuals can, under the right circumstances, grow into a stable group, especially if more people trickle in over time. Any smaller and random bad luck, disease, storms, a few bad birth years, can wipe them out before they get going. When archaeologists look at how quickly Australia seems to have filled with people, many reconstructions imagine either one relatively big founding pulse or several pulses that add up to something like that. The pattern on the ground, sites appearing across multiple regions within a few thousand years, fits a scenario where enough people arrived, often enough that the continent didn't have long empty zones for very long. Apply that to Flores. Whether the first crossing was accidental or deliberate, any successful colonization likely involved more than a pair of survivors. Our own species' later behavior suggests that to get a lasting signal, you want a group on the order of a small band or more. 10, 20, 30 individuals. And if crossings happened more than once, spaced over centuries or millennia, the effective founding population could be larger still, even if each raft only carried a handful. Lesson 3. Crossings don't have to be constant to be consequential. The early peopling of Sahul doesn't require daily ferry service. It requires a finite number of successful trips over a few hundred or a few thousand years. The frequency might be extremely low in human terms, maybe one successful group every few generations, but over deep time, that's enough. That perspective helps to soften the "it's too unlikely" objection to both accidental and low-tech intentional crossings in the deep past. If a viable group only has to make it to Flores once every, say, 50,000 years for a few million years, the long odds against any particular event don't necessarily make it impossible overall. Later humans remind us that even rare voyages can reshape continents, but here's where the analogy starts to wobble. Homo sapiens colonizing Sahul were operating in a world that looked very different from the one facing whoever first reached Flores 800,000 years earlier. Coastlines were different, sea levels followed their own rhythms, and climate patterns shifted. Ocean currents may not have flowed in the same directions or with the same strength. Wind regimes change on glacial and interglacial cycles, and the people themselves were different. By 50,000 years ago, Homo sapiens had a brain and body pretty much like yours. They had complex language. They made sophisticated composite tools, managed fire in subtle ways, and organized in social networks that could span hundreds of kilometers. They may have had exchange systems, marriage rules, and ritual obligations that stitched distant communities together. Those social and cognitive capacities make it easier to coordinate something as logistically tricky as a group sea crossing. You can plan ahead, gather food and water, select the crew, watch the weather, remember where previous voyagers landed. You can talk through the risks and tell stories about both successes and disasters. Earlier Homo, whoever made those old Flores tools, probably didn't have that full package. They were smart, but maybe in a different way. Strong spatial reasoning, great practical problem solving, but less capacity for dense symbolic culture, less verbal bandwidth to negotiate elaborate plans. Their toolkits were simpler. We have no evidence that they used bone or plant materials in complex composites the way later humans did, though that may partly be an artifact of what preserves. So if we take the Sahul precedent and simply push it back 800,000 years unchanged, we're overreaching. Different brains, different social worlds, different oceans. That doesn't mean the comparison is useless. It means we have to squeeze it for the few things that probably do carry over and leave the rest alone. Those carryovers look something like this. You don't need high culture to move over water. Basic curiosity, fear management, and motor skills are enough to experiment with floating things. Founding events are rare but powerful. A single successful crossing by a modest-sized group can permanently change an island's history. Even very low frequencies of success, 1 or 2 viable crossings in many thousands of years, can leave a big mark when you're looking back from the far future. And perhaps most importantly, once a population is established on an island, evolution and culture will go to work on it, shaping it in ways that don't necessarily preserve any clear record of how it got there in the first place. So when we look at Homo sapiens in Sahul and say, they clearly used boats, therefore the Flores hominins must have too, we're making too big a leap. But when we say, later humans show that even simple watercraft and modest planning can turn short straits into highways, that's a more reasonable parallel. It nudges the balance away from thinking deep-time island colonization is almost impossibly unlikely. It tells us that if early Homo could tinker at all, and if they had hundreds of thousands of years to do it in a landscape full of rivers, deltas, and near-shore islets, then deliberate short-range rafting is not out of the question. At the same time, the very differences between our world and theirs warn us not to lean too hard on that precedent. Our species made it to Australia with brains and cultures that were already the outcome of a long, unique evolutionary journey. The hominins on Flores belong to an earlier chapter, with their own constraints and possibilities. To get closer to their story, and to see just how weird island life can make a human species, we have to turn back to Flores itself, and to the tiny, baffling skeletons that rewrote the script on what island evolution can do. When Homo floresiensis was announced in 2004, it didn't just make headlines, it detonated. Because suddenly, Flores wasn't just the island where someone left old tools, it was the island that grew its own human species. In a cave called Liangbua on the western side of Flores, archaeologists uncovered a partial skeleton of a hominin adult. Skull, jaw, some limb bones. At first glance it looked like a child. The brain case was tiny, the body size small, the proportions odd. Then the dates came back. This child was an adult female about a metre tall with a brain the size of a grapefruit, who had been living on Flores around 60,000 to 100,000 years ago, and even deeper layers in the cave holding similar tools stretch back to almost 200,000 years ago. If those early tools on the island really are 800,000 years old, that means this wasn't some brief failed experiment. That means hominins got to Flores early, and at least some version of them hung on for something like 750,000 years. Long enough for evolution to run wild. The team that described the fossils argued that this wasn't a diseased modern human or a dwarf. It was a separate species, Homo floresiensis, quickly nicknamed the Hobbit. And if the stone tools scattered across Flores really do form a continuous story, then the hobbits weren't just island squatters at the end of the line. They were the latest chapter in a lineage that had been isolated there for so long that natural selection had quietly rebuilt them from the ground up. To understand what that means, you need one key concept: island dwarfism. Stick a big mammal on a small island with limited resources, no large predators, and a long time horizon, and weird things happen. Bodies shrink, lifespans adjust, reproductive strategies change, the entire energy economy of the animal gets rewritten to fit the new constraints. We see this over and over again in the fossil record. Elephants marooned on Mediterranean islands evolve into species the size of ponies. Hippos shrink. Giant deer get smaller. Sometimes the opposite happens too. Small animals get huge when predators are absent. That's island gigantism. Think giant rodents, oversized lizards, or the famous dodos and moa birds. Flores gives us both sides of the pattern at once. The island has a history of pygmy elephants, stegodons, that shrank dramatically compared to their mainland relatives. And alongside them, over time, you get these tiny humans. Homo floresiensis fits island dwarfism almost too well. Short stature, lightweight skeleton, small brain, small. Features that, taken together, look like a big-bodied ancestor put through the slow grinder of island life, until the design is optimized for scarcity. Because on a small island with fluctuating food supplies, having a big brain and a big body is expensive. You need more calories, you're more vulnerable to bad years. Selection doesn't care if you look impressive, it cares if you survive the lean seasons and raise kids. Shrink the body, shrink the brain, keep enough intelligence to make and use tools, and you might come out ahead. The question is, shrink down from what? This is where things get messy. When The Hobbit was first published, the lead hypothesis was that they descended from some early member of the Homo erectus family, or from a closely related archaic Homo. The idea went like this. An early big-bodied population of Homo, something like small Homo erectus, somehow reached Flores very early, maybe close to that 800,000-year mark when we see the oldest tools. Once there, cut off from other populations, they experienced strong selection for smaller bodies. Over hundreds of thousands of years, generation after generation, the island's limited resources, variable climate, and lack of large predators pushed their average size down. The largest individuals had a harder time surviving the worst droughts and famines. The smallest, most efficient bodies squeaked through, given enough time that can produce a new species, anatomically distinct, behaviorally adapted to island life, still recognizably human but no longer just small Homo erectus. That's one picture, hobbits, as the island dwarf descendants of the same kind of early Homo that may have first stepped onto that beach with stone tools 800,000 years ago. Another possibility is more radical. Some features of Homo floresiensis, the shape of the wrist bones, the structure of the shoulder, the feet, look oddly primitive. In some ways they seem more similar to much earlier hominins, closer to Homo habilis or even Australopithecines, than to classic Homo erectus. That has led to a fringe, but intriguing idea. What if a very early, small-bodied hominin somehow made it out of Africa much earlier than we thought, got as far as Southeast Asia, and then ended up marooned on Flores? In that scenario, you're not shrinking a big species, you're tweaking a small one and keeping it small. Most researchers are cautious about this. The fossil record outside Africa that far back is incredibly patchy. We don't have good evidence for pre-erectus hominins running around Indonesia, and it risks turning one weird fossil into an excuse to rewrite half of human dispersal history. So the majority view still leans towards something like early Homo erectus, or a close cousin, as the ancestor. The primitive traits in the Hobbit skeleton could be reversals, or the result of island selection unmasking variation we don't see well in mainland fossils. A third idea tried to dodge all of this. Maybe Homo floresiensis isn't a separate species at all. Maybe the skeletons in Liangbua are just modern humans with developmental disorders, microcephaly, dwarfism, or some combination of pathologies that made them small and strange-looking. If that were true, we wouldn't need island dwarfism or early arrivals. We could imagine a small recent community of Homo sapiens in the cave, and the weird skeletons as outliers in an otherwise normal population. The pathology hypothesis was attractive to some because it preserved a simple story. Only Homo sapiens in this region at that time, no late surviving archaic species, no small-brained toolmakers hanging around while we're already spreading across the globe. But over the last 2 decades, this idea has almost completely lost ground. For one, the hobbit skeletons show a consistent suite of features across individuals, not random deformities. The skull shape, wrist bones, jaws, teeth, and limb proportions line up in ways that match a coherent evolutionary design, not a one-off medical anomaly. For another, detailed comparisons with known pathological modern skeletons, including microcephalic individuals, don't match well. The hobbit brain is small, but its internal shape, as reconstructed from CT scans, is not just a shrunken Homo sapiens brain. It has its own pattern of folds and expansions, especially in regions linked to planning and tool use, and crucially, the tools associated with Homo floresiensis are not crude. They're part of a long local tradition of stoneworking on Flores, flakes, points, cutting edges shaped with skill and care. So most researchers today treat Homo floresiensis as a genuine, distinct human species. Pathology as a main explanation is now a minority view. That brings us back to the big picture. What does this tiny species actually tell us about islands, and about the mystery of how anyone got to Flores in the first place? First, it tells us that once a hominin population is established on an island, it can persist for an astonishingly long time. If the tool sequence on Flores is genuinely continuous from about 800,000 years ago through the time of Homo floresiensis, with some gaps, but no clear evidence that the island was completely abandoned and recolonized, then we're looking at something like 700,000 years of intermittent but ongoing human presence. That is deep time on a scale that's hard to even visualize. Count back from the present, past the rise of Homo sapiens, past Neanderthals, past the entire last glacial cycle, and Flores is still quietly doing its own human experiment. That endurance on a small volcanic island tells you that archaic humans were capable of stabilizing themselves ecologically in a limited environment. They figured out the local plants and animals, they handled periodic eruptions, droughts, and shifts in sea level. They kept knowledge moving across generations strongly enough that the basic toolkit didn't vanish. Second, it shows how violently isolation can reshape us. On the mainland, brain size in the Homo lineage generally trends upward over this time period. Bodies get taller and more efficient. Toolkits, where we see them, get more complex. The usual picture we tell is bigger brains, more culture, more success. Flores says, not so fast. Here is a hominin with a brain about 1/3 the size of yours, making tools, hunting pygmy elephants, and surviving for tens of thousands of years in a challenging tropical environment. Whatever we think intelligence looks like, evolution is clearly happy to take shortcuts when circumstances demand. Island life doesn't care about your big brain narrative, it cares about energy budgets and local problems. If a 30-kilogram body with a smaller brain does the job better than a 60-kilogram one with an oversized energy-hungry cortex, selection will gladly prune you down. Third, Homo floresiensis forces us to rethink what archaic really means. The hobbits are archaic in the sense that they're not Homo sapiens. Their anatomy is a mosaic of primitive and derived traits. But in another sense they're hyper-specialized and very recent. They were walking around while our own species was spreading across Eurasia. So you have this odd scenario. In some parts of the world you've got tall, big-brained Homo sapiens making art and elaborate tools. In others, Neanderthals practicing complex hunting strategies. And on Flores, a population of tiny, small-brained hominins descended from much older stock still napping away at stone flakes. If both the early tools and the hobbits really belong to the same island line, then Flores shows us something crucial about early sea crossings. However they first happened, accident, curiosity, makeshift rafts, once a population lands, the island takes over the story. The original act of crossing might have been rare, risky, and fundamentally similar for different hominin species. But what happens after you arrive can diverge dramatically. One island might turn its humans into seafarers who push further. Another might pin them down and miniaturize them until they're perfectly tuned for a tiny patch of land and go nowhere else. Homo floresiensis looks like the second case, not a stepping stone to empire, but a cul-de-sac where evolution parked a lineage and rewrote it around local constraints. And yet, their very existence on Flores is still a neon sign pointing back to that first, earlier mystery. They are living proof that, one way or another, hominins managed to cross deep water long before our species ever thought about Australia. We may never know exactly what their ancestors used: logs, rafts, floating debris, or how many attempts failed before one stuck. But the hobbits stand as a kind of fossil testimony, not to how they got there, to what islands can do to you once you arrive. Flores is the headline act: tiny humans, pygmy elephants, a tool record that might run back 800,000 years. It's the island everyone argues about. But here's the thing: Flores is not alone. Once archaeologists realized that at least one deep-water island in this region might have a shockingly long human story, they started looking harder at its neighbours, and slowly a pattern, or the hint of a pattern, began to emerge. Let's zoom out. The region between mainland Southeast Asia and Australia is called Wallacea. It's a giant jigsaw of islands separated by deep channels of ocean. Lombok, Sumbawa, Flores, Timor, Sulawesi, Halmahera, the Moluccas. Today it's a traveller's paradise. In the Pleistocene it was something much more important, an archipelago that should have been very hard for land-living mammals to cross. During ice ages, when sea levels dropped by up to 120 metres, the shallow shelves around Asia fused into a huge landmass called Sunda. The shallow shelves around Australia and New Guinea merged into Sahul. But Wallacea stayed broken. Deep basins between many of these islands never became dry land, no matter how much water froze into ice. If hominins, or any other large mammals, are turning up in Wallacea before modern humans, that's not just local weirdness. That's a regional signal that something about crossing water was happening way earlier than we used to think. Start with Sulawesi. For a long time, Sulawesi was a big blank spot on the map. Then, in the last couple of decades, archaeology there exploded. Rock art tens of thousands of years old. Hunting scenes, hand stencils. That alone already pushed back the timeline of sophisticated symbolic behaviour in the region. But deeper still, in the sediment layers of a valley called Wallanai, researchers found something different. Stone tools associated with extinct megafauna, and dates that might reach back beyond 100,000 years. Some claims even hint at activity approaching 500,000 years ago. These aren't as old as the most extreme dates from Flores, and the dating methods and contexts are still being debated. But the very fact that plausible pre-sapiens tools show up on Sulawesi changes the background picture. Because Sulawesi, like Flores, is not part of the Asian or Australian continental shelves. It's Wallacea. It's surrounded by deep water. You don't get there from Borneo or the Philippines just by walking out onto a glacial land bridge. At some point, somebody had to cross open sea, move east and south, and similar whispers appear. On Timor, another deep-water island, some sites show stone tools that may predate Homo sapiens' arrival. The dates and associations are murky, and not everyone agrees. But the pattern is familiar: simple but deliberate napped stones, found in contexts older than our species' clear presence. In the Philippines, on Luzon, there's the now famous Callao Cave hominin, Homo luzonensis, with bones dated to about 50,000 to 70,000 years ago. That's already evidence of another small-bodied, strange-looking human species on an island that required a sea crossing. Even more surprising, on Luzon there are cut-marked animal bones and stone tools that might go back more than 700,000 years. If those interpretations hold, Luzon joins Flores as a place where very early hominins somehow made it across deep water. So suddenly we're not talking about one rogue island. We're talking about multiple islands, scattered across Wallacea and beyond, each with hints, some faint, some stronger, that archaic humans were on them long before Homo sapiens showed up with advanced boats. But the moment you zoom out, the story stops being neat. On Flores, some researchers see a relatively continuous tool tradition, possibly stretching from around 800,000 years ago all the way into the time of Homo floresiensis, and maybe even overlapping briefly with modern humans. On Luzon, the gap between the very old butchered bones and the late surviving Homo luzonensis is enormous. On Timor and Sulawesi, early evidence is fragmented, patchy, sometimes contested. Instead of a tidy curve of first arrival, continuous presence, steady evolution, Wallacea gives us a mosaic. Bits of evidence popping up in different time slices, like static snapshots from a corrupted video. Some islands show possible early arrivals and no obvious later archaic species fossils. Others show late archaic fossils but only ambiguous early archaeology. In some places, like Sulawesi, we get spectacular later rock art that we know is Homo sapiens, laid on top of a more shadowy substratum of older tools that might belong to someone else. Is this one coherent story, a network of early seafarers hopping from island to island, or is it a series of independent one-off events? Did one successful crossing seed a regional expansion? Or did different hominin populations blunder their way across different channels at different times, leaving behind scattered, unconnected traces? Right now, the evidence can be read either way. To make sense of it, researchers don't just look at the stones, they look at the animals. Flores taught us that islands rewrite mammals. But the animals carry another kind of information too. They tell you who managed to get across the water and when. Take stegodons, those extinct relatives of elephants. Their fossils show up on several Wallacean islands in downsized form. We find dwarfed stegodons on Flores, on Timor, on Sulawesi. That means at some point, large proboscideans managed to get to those islands. But here's the key. Elephants and stegodons are surprisingly good at accidental sea crossings. They can swim long distances. During times of low sea level, when currents and shorelines shift, a small group can get swept off course or pushed out along a narrowing peninsula and end up on a new island. Once there, if they survive, natural selection does the island dwarfism trick. So stegodons tell us something important but limited. Wallacea was accessible to big mammals via rare but natural unplanned dispersal events. You don't need rafts or intelligence for them, just currents, storms, and time. Now contrast that with animals that are bad at crossing open water on their own. Large terrestrial carnivores, for example. Tigers and leopards never made it to Flores or Timor. Komodo dragons did, but they probably arrived much earlier and may have island hopped when sea levels and current patterns were different. Rodents, small mammals, certain kinds of lizards and birds can raft accidentally on mats of vegetation, but the odds of a stable breeding population establishing are low. So when we see certain faunal combinations, stegodons, giant rats, Komodo-like varanids, repeating across multiple islands, we're seeing a record of who nature can move by accident. That background gives us a baseline to ask a harder question. Did humans change this pattern? One way to test that is to look at timing. If hominin stone tools or bones appear on an island at the same time as a sudden wave of new animals that couldn't easily get there alone, that's a hint that somebody might have been moving them, deliberately or as camp followers. On many Wallacean islands, though, the picture is more subtle. Flores, for instance, doesn't suddenly bloom with exotic new mammals when humans arrive. Instead, it shows the slow-motion dance of an isolated ecosystem, responding to climate shifts and the gradual arrival or extinction of species like stegodons and giant rats. Homo floresiensis slots into that system as another player, not as a wrecking ball. So archaeologists look for other fingerprints of human impact. One is extinction timing. If a big, slow-breeding species disappears right after hominins show up, that's suspicious. On some islands, late Pleistocene and Holocene human arrivals line up almost perfectly with megafaunal collapse. In Wallacea's deeper past, it's less clear. Some stegodon populations vanish long before any firm evidence of Homo sapiens. Were archaic hominins responsible, Did volcanic eruptions or climate swings do the job instead? The dating precision often isn't good enough to make a clean call. Another fingerprint is dietary change in surviving animals. If, say, rodent tooth wear or isotope signatures shift abruptly around the time a new predator arrives, that might indicate changed vegetation, new fire regimes, or altered predator-prey dynamics. On Flores, there are hints that fire use and butchery by hominins shaped vegetation patches and influence which animals did well where, but the signal is faint compared to the sledgehammer effect of later farmers on other islands. A third line is the archaeology itself. Mass kill sites, piles of bones from a single vulnerable species, repeated burning of particular habitats. Those are the kinds of things we see when Homo sapiens roll into a naive island ecosystem. In Wallacea's early record, we don't yet see that kind of industrial predation. All of this points to a weird conclusion. If archaic hominins were crossing water to get to these islands, they don't look like the world-devouring ecosystem engineers that our own species eventually became. On Flores, Luzon, maybe Sulawesi, they seem more like careful opportunists who slipped into existing niches rather than blowing them up. And that, in turn, loops back to the bigger question. If these early island dwellers weren't radically transforming their environments, they might not have needed huge populations, dense settlements, or regular two-way seafaring. A small group could arrive once, find a way to survive, and then shrink into the ecological background noise. From the perspective of the island's fossil record, they'd be quiet. From the perspective of deep time dispersal, though, their existence is loud. When you take a regional view, the case for early crossings becomes both stronger and messier. Stronger because it's no longer just Flores whispering something is off with our old timelines. Luzon is whispering too. Sulawesi is clearing its throat. Timor and a few other islands are at least raising eyebrows. The odds that every one of these signals is a mistaken date, a misinterpreted rock, or a 1 in a billion freak event start to look low. Messier because the signals don't line up into a simple story of archaic Homo builds boats and conquers Wallacea. Instead, we get competing surprises. One island gives us tiny humans with old-fashioned bodies and a possible 800,000-year backstory. Another gives us a new species, Homo luzonensis, with its own odd mosaic of traits, but no clear early tool trail tying it to a deep crossing. A third shows hints of ancient stones in one valley and stunning sapiens rock art in another, but no fossils to say who did what, when. The faunal records line up enough to show us that big mammals could, in rare cases, cross these seas without brains or boats. At the same time, the hominin bones and tools suggest that, somehow, our cousins were doing something more directed. Not necessarily shipbuilding, not necessarily navigation in the way we understand it, but repeated non-random contact with islands that should have been hard to reach. A regional view forces us to hold two truths at once. First, that Wallacea was never an absolute barrier. Currents, storms, and sheer geological time have always been capable of shuffling genes and species across deep channels. Second, that by at least 800,000 years ago, and maybe earlier, members of our broader human family were part of that shuffle in a way that looks less like driftwood and more like deliberate risk. Whether that means rafts clinging to storm debris, seasonal forays along coastlines, or something stranger, we still don't know. But step back far enough, and Flores stops being an isolated anomaly. It becomes one tile in a larger fractured mosaic. And the more tiles we uncover across Wallacea, the harder it gets to explain them all away without admitting a possibility our textbooks weren't ready for. Long before Homo sapiens ever dreamed of open water, other humans may already have been out there, edging along the coastlines, crossing unseen channels, and quietly redrawing the map of where a land animal could live. And that mosaic, incomplete as it is, sets the stage for the next problem. Because if the islands, the tools, the animals, and the bones together are whispering that early humans were better at crossing water than we thought, there's still an uncomfortable question. Why, with all this evidence, can't science yet agree on how any of it actually happened? Because right now the most honest answer is, we're staring at the outline of a story without the middle chapters. We can say that somebody reached Flores by around 800,000 years ago, we can say that other impossible islands in Wallacea and beyond start lighting up with hints of archaic humans long before Homo sapiens. We can even sketch the broad conditions of the ancient oceans, the likely coastlines, the kinds of animals that made it across. But the crucial pieces, the who, the how, and the why, are still mostly blank. Start with the roots. On a modern map, you can draw all kinds of arrows from mainland Asia down through island chains toward Flores, Timor, Sulawesi, and on towards Sahul. But 800,000 years ago the world looked different. Sea levels were lower, sure, but not in a simple, everything's connected way. Some channels narrowed, others shifted, some coastlines stretched out into the sea like long fingers, currents rerouted, islands merged and split. When you try to reconstruct that world in detail, you run into two problems. First, precision. We can estimate global sea level pretty well, but local shorelines, those depend on subsidence, uplift, sedimentation, volcanism, messy place-by-place geology. A few meters of vertical change can move a coastline tens of kilometers. So when archaeologists say, this crossing would have been 20 kilometers at minimum, or that channel never closed, that's based on best fit models, not a high-resolution map we can check against reality. The broad picture, deep basins stay deep, is solid. The exact stepping stones a small group of hominins might have used, that's still mostly guesswork. Second, time. These crossings didn't happen once. They would have been possible only during certain climate phases, when sea level, currents and wind patterns lined up just right. We don't yet know which windows mattered most. Was the crucial crossing into Flores tied to an especially long glacial low stand? Or did it happen during a shorter, more chaotic transition, when storms and currents were at their most extreme? The tools give us age ranges that can span tens of thousands of years. Climate proxies give us curves, not calendars. Lining those up precisely enough to say, they probably went this way, at this time, under these conditions, is still beyond us. Then there's the question that keeps coming back like a tide. Accident or intention? If a small group of Homo erectus-like hominins ended up on Flores or Luzon or Timor, did they get there because they built something that floated and pushed off on purpose? Or did a storm rip up a section of coastal forest, shove it offshore with a bunch of terrified animals and a few unlucky bipeds clinging on, and deposit the whole mess on a distant shore? Both scenarios are physically possible. We know that natural rafts can move animals across impressive distances. We also know that later humans, long before steel hulls and GPS, learned to read currents and winds well enough to ride those same systems deliberately. What we don't know is when that shift from passenger to pilot happened. The evidence from Wallacea refuses to settle the argument. On the one hand, the pattern of multiple islands with hominin traces suggests something more than a freak, once-ever storm event. It looks like either repeated accidents or at least occasionally successful attempts. On the other hand, the archaeological record we have from those early periods is quiet. No dense sites, no obvious signs of large populations, no clear footprints of regular two-way traffic. If there were intentional voyages, they might have been rare, opportunistic pushes rather than a routine ferry service. That ambiguity bleeds directly into the third unknown. What, if anything, were they travelling in? We can infer a lot from later prehistory. By 50,000 years ago, Homo sapiens was definitely crossing water with some kind of boats or rafts. By 40,000, people are reaching Sahul. By 30,000, there's evidence of repeated crossings in the Mediterranean. But those technologies, even the simplest dugouts or lashed log rafts, leave almost nothing behind in tropical coastal settings after a few thousand years, let alone hundreds of thousands. Wood rots, plant fibres decay, simple paddles, poles, or woven floats disintegrate. The places where these things would have been built and stored, sandy beaches, estuaries, coastal flats, are the worst possible environments for preservation. And that brings us to the main reason science still can't close the case. The record we're trying to read has literally been drowned. At the height of glacial low stands, global sea levels were more than 100 meters lower than today. The beaches, coves and river mouths where early humans would have gathered, fished, experimented with floating logs and maybe pushed off toward the horizon. Most of those are now underwater, tens of kilometers offshore. The campfires where people might have debated whether to risk a crossing, the places where a crude raft was dragged up and patched after a terrifying voyage. If they existed, they're now buried under meters of sediment on submerged continental shelves and island margins. On land, we're already dealing with a sparse, biased record. Tropical soils chew up bone. Erosion strips away older layers. Volcanic eruptions bury sites beneath lava or ash. Human occupations that were brief, low density or intermittent leave only the faintest traces, a few flakes of stone, a butchered bone or two, a single tooth. Most of that never gets preserved. Of what's preserved, most is never exposed. Of what's exposed, only a fraction is ever excavated. That's the part people often underestimate. Archaeology isn't like reading a book with missing pages. It's more like scanning a burned library for any leftover scraps at all. Flores has a handful of caves and river valleys that have been carefully dug. Sulawesi has a few key basins and shelters. Luzon, Timor and other islands each have a tiny constellation of studied sites compared to the vast area that's still unexplored. When you realise that our whole idea of early island crossings is built on a few scattered discoveries in a few square kilometres across millions of hectares of land and drowned shelf, the gaps stop being surprising. The surprises do. So what would actually count as a game changer? What kind of discovery would let science move from something odd happened here to this is how they did it? One obvious candidate is more sites, but not just more of the same. We need contexts that fill in the blanks between first arrival and much later. For Flores, that means finding occupations between the oldest tools and the time of Homo floresiensis that are clearly connected, or clearly not. For Luzon, it means something that links the 700,000-year-old butchered rhinos to the 50,000-year-old Homo luzonensis remains. If we could trace a continuous occupation or a pattern of repeated visits, that would tell us whether we're dealing with a rare one-off accident or with populations capable of maintaining island lifeways over deep time. Another kind of decisive evidence would be older tools, or bones, on islands we haven't even flagged yet as problematic. Imagine stone tools clearly older than 1 million years on a deep-water island with no possible land bridge, securely dated with multiple methods. Or hominin bones from a Wallacean site that show clear morphological ties to a specific mainland population, say, a group related to early Homo erectus in Java, pinned down tightly in time. That kind of find would force us to connect specific dots. These people, from this region, were over there by this date. Better dating alone could wield huge leverage. Right now, some of the most controversial claims hinge on broad or overlapping date ranges. A few tens of thousands of years sliced off or added on can flip a story from plausible crossing during a known low stand to requires a very different ocean scenario. Improvements in luminescence dating, uranium series methods, and cross-checks with independent climate proxies could tighten those bands. If the earliest Flores tools, for instance, shifted significantly older or younger within the plausible range, that might either demand an even more radical view of early seafaring or bring them into line with a more conservative set of routes and conditions. Then there's underwater archaeology, the big wild card. If we ever start systematically exploring the now submerged coastlines of Sunda, Wallacea and Sahel with the same intensity we apply to land caves and rock shelters, the entire conversation could flip. Submerged paleo shorelines might preserve drowned river mouths with buried campsites, middens, or even patterns of lithic discard that scream coastal foraging group lived here. In cooler or less biologically active waters, there's a slim chance of preserved wooden artifacts, stakes, fish traps, maybe even fragments of watercraft in anoxic muds. Even without direct boat remains, a dense cluster of tools and food remains on an ancient shoreline exactly opposite a deep channel island might be hard to explain without some kind of intentional crossing. To get there, though, archaeology has to keep leaning on and arguing with other sciences. Geologists model uplift and subsidence to rebuild vanished coasts. Oceanographers simulate past current systems and wind patterns, asking which drift paths are likely, which crossings would have been death traps, and where a simple raft would most often end up. Paleoanthropologists look at bones and teeth, comparing island hominins to mainland relatives, trying to infer how mobile they were, how they used their hands, how their brains might have been wired for planning and risk. Archaeologists read the stones and the sediments, parsing minute patterns of breakage and transport, looking for the difference between a naturally smashed rock and a deliberately shaped tool. These fields don't always agree. A paleoanthropologist might argue that a small-brained, thick-boned Homo erectus-like ancestor couldn't possibly have managed open water crossings intentionally. An oceanographer might respond that certain current systems could reliably ferry floating debris from one island to another, making accidental crossings plausible. An archaeologist might counter that the repeated presence of tools on multiple islands, in multiple time slices, looks a lot like a behavioural pattern rather than random drift. A geologist might throw in a curveball by showing that a supposedly permanent deep channel was briefly narrowed by local uplift 900,000 years ago, changing the risk calculus entirely. It's in those arguments, in the back and forth over models, dates, sites and bones, that our picture of early seafaring slowly sharpens. No single discipline can solve it. You need everyone at the table, comparing their imperfect pieces of the jigsaw, and that's why the next few decades could be so disruptive. Remote sensing is getting better at spotting buried landforms and ancient river deltas, both on land and underwater. Autonomous underwater vehicles can map seafloors and even collect samples in places that were unreachable a generation ago. Improved dating techniques are already forcing revisions at some classic sites. New field projects in underexplored parts of Wallacea, the Philippines, and the Indian Ocean are starting to treat islands not as odd side notes, but as central testing grounds for human dispersal. It's entirely possible that right now, in some unexcavated valley on a Wallisan island, there's a stratified site that holds exactly what we're missing, a sequence of tools, bones and sediments that shows a clear arrival, a clear continuity, and maybe even signs of coastal adaptation. Or that out on a drowned shelf, a buried shoreline is quietly preserving the remains of a campsite from 700,000 years ago, waiting for the first sonar survey to light it up. When those pieces start to fall into place, the story of that first crossing to Flores, and all the others like it, will change from a hazy somehow into something sharper. Not just that early humans got there, but how risky it was, how rare or routine, how much planning it took, and what kind of minds were making those decisions. And that, in turn, sets up the last question we still have to face. Even if we someday know the routes, the timing, maybe even the kind of craft they used, what did that first ocean crossing actually feel like to the people who lived it? And what did it mean for every voyage that came after? So we circle back to that shoreline, 800,000 years ago, with almost everything we've learned and still no clean answer. Here's what we actually know. We know that by around that time, some kind of human, probably Homo erectus-like, maybe something a bit different, was living on islands that should not have been reachable on foot. Flores, Luzon, maybe others we haven't even identified yet. We know they were there because the stones don't lie. Flaked tools, shaped edges, cut marks on animal bones. Someone was hitting rocks together on those islands long before our own species existed. We know the ocean between those islands and the mainland was never a friendly little stream you could wade. Even at the lowest sea levels, there were deep channels, strong currents, real blue water. Not a continent-spanning ocean, but enough that, oops, we tripped and fell onto this island, isn't an obvious explanation. We know later humans, Neanderthals, Denisovans, and especially Homo sapiens, learned to treat water not as a boundary but as a highway. By 50,000 years ago, people were absolutely using some kind of watercraft to reach Sehol. By 30,000 years ago, people were moving so regularly across the Mediterranean that some islands looked like they had ferry schedules. Seafaring is not a late add-on to human behaviour. It's baked into the story surprisingly early. We know that the tools and bones on these early islands don't scream huge, thriving maritime civilization. They look like small populations, thin traces, long gaps in the record, enough to prove presence, not enough to prove intent beyond doubt. We know that the coastlines where the best evidence would have been preserved are mostly gone, sunk under post-glacial seas. The workshops, the fish traps, the driftwood experiments that finally worked, if they ever existed, are probably out there under silt and coral, not waiting politely in cave floors for archaeologists to trowel them up, and beyond that. We're in the domain of suspicion, not certainty. Many researchers suspect that at least some of those crossings were intentional. Not in the sense of GPS coordinates and nautical charts, but in the sense of a group of hominins learned that if you cling to logs, or bind a few together, or push off at a certain tide, sometimes you don't die. Sometimes you end up where the horizon used to be. Over generations, that sometimes got slightly less terrifying and slightly more predictable. Others suspect that the earliest crossings might still have been freak events. Forest rafts torn loose by storms, tsunamis sucking entire shorelines outward, groups that didn't decide to voyage so much as survive something horrible and wake up somewhere new. In that picture, intentional seafaring evolves later, inspired by what drift and disaster had already proven was physically possible. And then there's the in-between position, that the line between accident and intention is blurry. Maybe early humans didn't set out to cross a known channel to a mapped island. Maybe they were following a river mouth, riding a flood, exploiting a seasonal current they barely understood. More like getting caught in a riptide you half expect, less like booking a one-way ticket. The frustrating part is that all three scenarios are compatible with the evidence we have. Accidents can be rare but real. Intentional experiments can leave almost no trace on bad preservation coastlines. Small maritime traditions can rise and fall without ever ballooning into the dense, obvious populations that fill the archaeological record later. So, after all that, the ocean crossing at the heart of this story is still unanswered. Not unanswered in the sense of we know nothing. We know a lot more than we did a few decades ago. We can bracket time windows, model currents, compare island bones to mainland ancestors, estimate how many individuals you'd need to found a viable population. We can say, this route was more likely than that one. This crossing window lines up better with the dates. These toolkits look just plausible enough for coastal foragers who occasionally push beyond sight of land. But we still can't point to a single moment and say, here, this is where a group of pre-sapiens humans stood on a beach, looked out over a deep channel, and decided to gamble their lives on wooden water. And maybe that's where you come in. If you've stayed with this story all the way here, you probably have a favourite theory. Do you lean toward the big storm raft idea? Do you think they were deliberate pioneers, reading wind and current more cleverly than we give them credit for? Or do you see it as something messier, a long, stumbling learning process where intention and accident blur together? Tell me what you think in the comments. If you were standing on that ancient shoreline with only stone tools and fire, and you knew there was land somewhere beyond the horizon, what would it take for you to step onto a floating bundle of logs and push off? And while you're down there, let me know where you're listening from. One of the fun things about these deep time stories is that they're being heard in real time all over the modern world. From coastlines, those early humans once walked to inland places they never imagined. If you found this journey through prehistoric oceans interesting, it really helps if you like this video, leave a comment, and subscribe to the channel. That's how more people find these strange little corners of human history, and it lets me keep digging into puzzles like this one. If you want to go even deeper into mysteries like the 800,000-year-old crossing, lost species, vanished coastlines, forgotten experiments in being human, I've put a lot more of them into a book all about prehistoric secrets and the evidence behind them. You can read more about it and pick up a copy at sleepytimehistory.com. Until then, the unanswered crossing is going to stay exactly where it's been for hundreds of thousands of years. Out there, between the last visible shoreline and the first faint line of land, somewhere beyond the edge of what we can prove, and right in the middle of what we most want to understand.